I'm Eckhard Hitzer. I'm talking today on the inner product of two oriented points in conformal geometric algebra. And at the beginning, I want to make some acknowledgements. I take a quotation from the Bible. Mary said at the beginning of Luke, Ecce ancilla Domini, means I am the Lord's servant. Now, I dedicate this to my family, to my colleagues, Werner Benger, Dietmar Hildenbrand, Marfriede Wieser, organizers of this conference, and also a special thanks to the sponsors of the conference. The research I do under the Creative Peace license, you see the link here, and special education is to the children who died in the excess deaths among children, 700 to 1,600% since the European Medicines Agency approved the COVID vaccine for kids. So I'll give an introduction, then show a range of examples, then talk about a particular term in the inner product result, symmetries of the inner product, and the inner product of oriented points in n-dimensional Euclidean space, so generalize it to n dimensions. Now for introduction, we apply conformal geometric algebra to the description of points, including points with planar orientation. As a reference, I recommend 14 and engineering tutorial 11. Free software there's a toolbox, is MATLAB. So I've done computations for this talk with this toolbox. Alternatively, you could use Galop. Introduction to conformal geometric algebra, these two references are 2 and 5. And again, Galop is an efficient implementation. So CGA has wide-ranging applications in physics, quantum computing, molecular geometry, and so on. And most of it has already been presented, at least with a few nice examples in this conference. Extensive surveys are these 3 papers, which you find in the reference list. And the notation of, or the notion of oriented point is in paper 6. That's in 2011 by Dietmar Hildenbrand and a student of him, Patrick Chaillet. It may have potential application, for example, for LiDAR strip adjustments. Now, what is an oriented point? It is a multi-vector expression of a circle with radius 0 in conformal geometric algebra, and it's dual. So it's Q and is basically given by IQ, and IQ is a bivector showing the orientation of the plane of the point, and Q itself is the 3D position in 3-dimensional space of the point. And Q star is a dual expression, and in the dual expression you can simply replace the bivector IQ by the normal vector NQ normal to the bivector IQ. Now, a traditional conformal point without orientation, therefore I write NO, no orientation, and it has the index NO. It just means, as you see here in equation 3 at the left side, a conformal point as you're used to, only given by the position in 3-dimensional space. Now, if you take from equation 1 the oriented point and you add this radius term, you end up with the expression for a circle. That is the right side of equation 3. The Euclidean bivector IQ, that is the kind of carrier plane orientation of the circle or of the oriented point, you get with these expression, take the outer product with E infinity and then right contract with E, the bivector of the origin infinity plane. And also from the circle or from the oriented point, you can get the conformal point at the center or at the position of the oriented point with the sandwiching operation. The hat means the great involution. So you just sandwich between c hat and c infinity, or correspondingly between q hat and q. From it, it's very easy to extract the Euclidean position vector in Formula 6. And you can also get the radius by simply taking c times the great involution of c, and you divide to get the number right with IQ squared. Yeah, and we had the conformal point Q. We take a second conformal point P, and we conveniently position it at the origin. So P is the position vector is 0. And then the expression is very simple. It's just IP, the bivector times E0. Now we compute the inner product. And this is a scalar part of the geometric product. And we find it's a relatively simple expression, number 9 here, minus 1/2 q squared IP dot IQ, the inner product, minus the inner product of Q with IP times the inner product of Q with IQ, and takes scalar part of that. Now, P is positioned at 0, and therefore Q becomes the Euclidean distance vector of the point P to Q, so distance between P and Q. The inner product P dot Q is invariant under CGA motion operators, and that generalizes the result we get on the right side of equation 9 to a point pair in general position and in general orientation. So we can always replace for any position of P and Q the vector Q in equation 9 by the distance vector between the positions of the 2 points. So therefore, you can freely replace Q by D, which is Q minus P, if P is not 0. Now, this is the algebraic relation for the bivector and its normal direction. So just multiply the normal direction by the E1, E2, E3 trivector of Euclidean geometric algebra, and you get the bivector IQ and correspondingly IP. And if you insert this, then the second term we had in equation 9 can be expressed with np dot nq minus q hat dot nq, and second is q hat dot np, and this is just a scalar term in square brackets. And q hat is this unit distance direction. So q squared is the square of the distance. And now you can also use this identity that based on 10, IP dot IQ is minus NP dot NQ. Now the inner product of 2 oriented points, as we see from the 3 inner products in the result, depends only on 3 angles. So the angle between NP and NQ we call, as you see in the diagram below, alpha PQ. That is basically the dihedral angle between the 2 planes of orientation. And then we have the angle cosine theta P and theta Q. And these are the angles between the distance vector and the normal vector NP, and the distance vector and the normal vector NQ. And naturally, because the tips of the 3 vectors form a spherical triangle, the angle alpha PQ is limited between the absolute value of theta P minus theta Q, and it cannot be more than theta P plus theta Q. Yeah, and if you plot P dot Q as a function of the angles, then in this diagram we have one x is theta p from 0 to pi and half, and the other is theta q from 0 to pi half. And you could plot it over minus pi half to plus pi half over the whole plane, and would just be symmetric to the three other quadrants. And it's nicely increasing to where the angles are theta p and theta q are 0. So when it's fully aligned, the two planes are parallel and are orthogonal to the distance vector, and you can use gradient ascent to get there basically from anywhere, no matter what is the angle alpha pq. And yeah, so that could be used for for machine learning optimization or adjustment. Now, two special cases. One is what is the expression? How does it simplify? If simply the two planes are parallel, the two orientations are the same, np and np again, then p dot q simply becomes 1/2 q squared cosine 2 theta, which is now the single angle between the distance vector and the orientation vector. And furthermore, if the planes are not only parallel, but they are orthogonal to the distance vector, then it's further simplified to 1/2 q squared. And it's pretty similar to the inner product of conformal points at the same position. It just has a minus sign. But you can get it if you flip one of the vectors. And now I present these 7 examples. Now, the first example is what we have just seen, the full alignment. So all vectors are parallel. And then what is the general result is you get the distance squared, which is 3 divided by 2. And here we are in one plane, and the distance vector is also in that plane. And in that case, the result here is a -1, and it is the same result when I put the conformal point p no instead of p and q no instead of q. So in this case, the result is the same, but you get from the inner product of two conformal points in the same position. And here we have now two parallel planes, and the angle theta is pi over 4, and this is a bit a special angle. In that case, it also comes out to be 0. Now here we take not pi over 4, but more general angle theta. So the distance vector is 2e2 plus 3e3, and then the result is non-zero, and we get 5/2 in this case. Now we have the case of the two planes being mutually perpendicular. They are orthogonal to each other, and the distance vector is in one of the two planes and orthogonal to the other plane. And in that case, we always get 0. And this is the same situation. We just have rotated the NP vector around the axis formed by the distance vector, but the result doesn't change. It's still 0. And here now we have the two planes are tilted relative to each other with the angle pi over 4. And if you go through the computation, we get 9 over 2 square root 2. Now, both terms contribute, but the second term, cosine theta p, cos theta q, that is dominating. Now, about the symmetry of this expression in equation 9, if the two planes are not parallel, so NP and NQ are not parallel, then together they define a plane bivector. And we can split the distance vector into a component parallel to the plane and orthogonal to the plane. And then in the computation, the inner product with the orthogonal component drops out because it's orthogonal to both NP and NQ. If the two vectors are the same, so the orientations agree, then we can split Q into a component perpendicular to this vector and parallel to it. And again, the perpendicular component drops out in the computation. If the distance vector is orthogonal to both vectors, then we always get 0 from this term. And if the NP and NQ are the same and Q points in the same direction or opposite, so distance vector points in the same direction or opposite, then we get the same result like having two conformal points in the same positions of P and Q. And as you know, the inner product of two conformal points always gives -half the distance squared. So it's the same up to a sign in equation 34. And if the two vectors have the same direction but opposite sign, so NQ is -NP or -NQ is NP, and the distance vector is in the same direction, so everything is aligned, then as I said before in the example, we get exactly -half Q squared, which is the same like taking two conformal points in the same position, even the sign agrees then. And as for the symmetry of the expression, the three vectors, there are the arguments, three arguments of the inner product expression. So I call it just f, a function of NP, NQ, and Q hat, the direction of the distance. And if I change the sign of NP or NQ, I change the overall sign. If I change the direction, reverse the direction, the inner product is the same. And if I change the order of NP and NQ, it's also symmetric under that change. So changing the sign of NP or NQ changes the sign of the inner product, and the relative sign of NP and NQ therefore determines the overall sign of P dot Q. Changing the order of the two leaves the inner product invariant, and reversing the distance vector leaves it invariant. Now we can easily, in one slide, generalize to n dimensions. So we take CGA for n-dimensional Euclidean space, and then the vector NP, which was a vector in 3 dimensions, is now a vector in n dimensions, and it is normal to the n-1 dimensional orientation hyperplane of the point. But the expression otherwise is just the same as we had before for the oriented point. Then we can compute the inner product, and we get also the same result, only there is a sign factor plus or minus in the beginning, depending on the dimension of the space. And if the dimension is 3, we have the same result as we had previously. Yeah, so I conclude, I refute circles and oriented points in CGA, then the inner product of two oriented points in terms of the distance vector and the point orientations. Then we looked in the geometric meaning with the help of examples, and then also the symmetry of the expression and generalized to n dimensions. It may be applicable to lidar strip adjustment, where points on overlapping strips need to be compared, including their local plane orientation of the respective strip. Yeah. So this is kind of advertisement slide. You can subscribe to the GANet. It appears 5 or 6 times a year. It has information about conferences and publications, etc., or software. And there's also this blog, which I recommend. And I published this book last year. And so if you're interested, you can still buy it until the end of this year with this code QCFT25, and you get a 25% discount. Then I want to invite you to the conference next year in June in Holon in Israel, Holon Institute of Technology, International Conference of Algebra and the Applications in Mathematical Physics. And next August, there is in Shanghai a workshop called Engage. And it's like novel graphics for like novel GA for graphics and engineering is the meaning. Yeah, it's a workshop in a main computer graphics conference. So here are the papers. In this paper 6 by Dietmar and Patrick, you find the original notion I used for oriented point. Yeah. Okay, so that's the end of my presentation. Thank you very much for your attention. So I'm open for questions.
Any questions for Eckhard?
Hi, Anthony Lazenby here. You would think that if you include orientation, you should pick up extra information and have that extra information available, as well as the original distance between objects. But in several cases, your P.Q gives 0. And doesn't that look like you're losing information?
Yeah, it's because it's a combination of information, and depending on the situation, there are particular situations when it's 0. But I mean, you always have the individual points, and as I showed previously, you can from each point extract also the conformal point, which corresponds to it position-wise, and then you can at least compute via the inner product the distance vector, the actual distance as well. Yeah, and I mean, the possible application I was thinking about for LiDAR, you have the orientations of the 2 planes when you want to compare them already within an angle of some 5 degree, etc. So you're already close to the optimum, and then you're not in danger of getting 0 in the end. Yeah.
Eckhard, thank you. It's Joan Lazenby now.
Yes.
So effectively, if I understand it, if I have a sort of little unit planes at different points in space, you've got a scalar measure of, distances, in quotes, between those planes. Yes?
Yeah, it's a sort of involved measure. Yeah. But
it's an orientation. This is precisely what Alberto's using as input to his neural network. We need to extract a scalar, and we use it, we get something by the rotations in conformal space between planes. But it'd be interesting to see if your method, we build up a scalar map, gives anything differently.
Yeah, I think it would be interesting to see it tried out in a real world problem. Yeah.
Okay.
Mm-hmm.